Hello everyone, this is Dr. Young, and in this video we're going to talk about acid-base reactions and just introduce you to what they are and how to identify them. So you may have heard of acid-base reactions before. There's lots of common real-world examples. Many of you may have made baking soda and vinegar volcanoes. It's involved in tooth decay, right? When you get cavities and you have acids forming on your teeth to dissolve the enamel and everything. You may know people, or you maybe take stomach antacids, or you've heard of ocean acidification due to global warming, limestones getting eroded, your blood pH, or just pH in general, right? It's all a measure of acidity. And so I have these three examples down here, right? I just want to talk to you about some of these. So like in this first one, the idea is that we have this acid, which is just represented as an H+, and then something called sodium bicarbonate, right? So sodium bicarbonate. More commonly known as baking soda. And this is participating in an acid-base reaction, right? This is kind of be like what happens in your vinegar volcano type of thing. So you have these reactions, you form sodium, you got carbon dioxide and water, and you see a bunch of fizzing and stuff, right? You also have examples of acids, again, H+, reacting with something like calcium carbonate. So that's in this example down here. So here's calcium carbonate. Let me write this out a little bit better. So calcium carbonate, which is what makes up, which is what you find in antacids. It's one of the main things. It's not the only thing, but antacid, it's one of the big ones, so antacids. Also found in the shells of a lot of sea critters. Right, so different kinds of planktons and then actual things that you think of that have shells. It's also what makes up limestone. Calcium carbonate's a lot of things. It's chalk. It's all kinds of things. So here's another acid-base reaction in which calcium carbonate reacts with acids to these things. And right, so the idea is that when you have acidification, it can affect all of these things. Right, if you have too much stomach acid, you eat calcium carbonate to react with that acid so that you don't have as much stomach pain. Because of ocean acidification, of the increase of CO2, you have more acid in the oceans, and that seems to deteriorate things that rely on calcium carbonate shells, whether they're certain types of corals or, like I was saying, the plankton and stuff, start to get all chewed up, which is a really bad thing. And then things like limestone, like acid rain. You may have heard of acid rain dissolving, either actual limestone quarries or dissolving out dams or ruining statues, etc., stuff like that. But that's all acid-base reactions. And then lastly, we might see examples like this one down here, more of an organic-y example where our group, right, is just some general residue group, some random thing. But if you have an amino group versus a carboxyl group, right, we talked about how carboxyls are acidic, and they have these hydrogens that can pop off of them, and amino groups are basic, which means they want to pick up those hydrogens. And here, as you look on the right-hand side, sure enough, we have an extra hydrogen here and that positive charge, so it picked up that H+. And so we did an acid-base reaction right there. And if you look at all of these, right, what they all have in common is that the definition of an acid-base reaction is a transfer of a proton. And H+, right, is just is a proton. So anytime you just transfer an H+, you just transfer a proton, that is an acid-base reaction. All acid-base reactions transfer protons. Anytime you transfer just a proton, it's an acid-base reaction. So let's look at this a little bit more specifically, right? Here's an equation, a classic equation. So right, remember that we're talking about a transfer of a proton. That's what the definition of an acid-base reaction is. And so in this example, right, one of the ways that you're going to see acid-base reactions is they're going to be kind of like a type of double replacement reaction. And by double replacement, what I'm saying here is that you're going to take your two cations. So in this case, here's a generic AB and a B and a CD. The idea is that you're going to replace those two things. So now your A is going to be with your D, and your C is going to be with your B, right? That is a double replacement. So now we have the A and the D together, and we have the C and the B together, right? So we've switched the two cations. So switch the cations. And remember that the cations are the things that are first, right? If you're like, wait, which one's the cation? How do I know? Remember that the cations in ionic compounds are always the first thing, anions are always the second thing. So switch the cations, the positive things. And if you look up here, that's sure enough, that is what we do, right? If I look at what the cations are and anions are here, right, it looks like for HCl, my cation is H+, my anion is Cl-. For the NaOH, my cation is Na+, plus and my anion is OH minus. And so what we're saying here is that in acid-base reactions, right, when you have these types of equations written out, they're just double replacements. So now I should have my H with my OH and my Na with my Cl, right? I'm going to do a double replacement. And sure enough, that's what we see, right? We said that the Na should now be with the Cl. That's what we've got. And then we said that the H plus should now be with the OH, which is what we've got, right? Water's HOH. It's like hydrogen hydroxide in a way, right? H2O. So you're just doing a double replacement between the two of them. You're just switching those cations, right? So anytime you have a double replacement where one cation is an H plus, that is an acid-base reaction because you transferred a hydrogen from one thing to another thing. As far as our definitions go, right, acid-base reactions, the idea here is that an acid is just the thing that donates the proton. Whatever donates the proton is the acid. Donates a proton. So in our example up here, right, HCl was the thing that donated the proton, so it's the acid. Donates the proton, therefore this is the acid, right? Here's the proton that we're talking about, that H plus. Versus the base is just the thing that accepts that proton. So bases accept. They accept it or they pick it up, accept a proton. So if you look at this thing over on the right hand, right, it's the hydroxide. That's where the proton ended up. So it's the OH, the hydroxide, that accepts the proton, making it the base. And right, of course, in acid-base reactions, you're always going to have an acid. You're always going to have a base. Right, so one thing needs to donate the proton, one thing needs to accept the proton. And again, most of your examples that you're going to see are going to be these double replacements. But really, any time you see a transfer of a proton from one thing to another thing, that's an acid-base reaction. Let's look at a couple of examples. So I have all of these. Right, so again, I'm going to kind of write this out here. So I've got KOH and H2SO4 make K2SO4 and 2 H2Os, right? So potassium hydroxide, hydrogen sulfate makes potassium, sulfate, and water. If I look at this and I want to know, is this first example an acid-base reaction? Again, what I'm looking at is, did I just replace the cations? So in this case, my cation was K+. In this case, my ion was H+. And the question is, did I simply switch those two? Is my K+ now with the sulfate? Or in other words, is my H plus now with the hydroxide? And if I look over here, sure enough, right, my K plus is now with the sulfate, so I did switch those. And if I look at the other thing, right, again, I made water, right? Now my H plus is with OH minus, so now I have water. So this would, in fact, be an acid-base reaction. Right, or in other words, I transferred an H plus, right? It looks like this was the thing that acted as the acid because it had the H plus that it gave, and that this would be our base. It's the thing that accepted the H plus. So I did have that double replacement. If I look down at the second example, right, I looked at the second example, I've got hydrochloric acid, I've got HCl and zinc, make zinc chloride and H2 gas. And if I take a look at this, right, definitely I've got, let me go ahead and write this H plus, I've got my H plus, and my HCl, but then I just have zinc. It's not an ionic compound. I don't see it split up. There's no cation and anion. It's just one thing. And so even though definitely HCl is considered an acid, it's a strong acid, it's not transferring its H plus to something. In fact, the hydrogens still stay together, right? If you look over here, the hydrogens are still together. It is not a, it didn't transfer to anything else. It didn't transfer to a base. So this would be a case in which we do not have an acid-base reaction. This is not an acid-base reaction. Not an acid-base reaction. Because there was no transfer of that H plus to something new, right? It just stayed with itself. It didn't transfer. There's no cation and anion here, right? So HCl in this case, while it is considered an acid usually, it did not act as an acid. This is actually a redox reaction. We're not going to talk about it right now. But if I look back down here at the third example, I've got HNO3 and sodium bicarbonate, make some stuff. But again, if I want to check if this is acid-base, I need to ask myself, okay, did this H plus switch places with this Na plus. Right, that's what I need to know. And so did my H plus end up with the bicarbonate, and did my Na end up, whoops, let's go back a step. Did my sodium, did my Na end up with the nitrate? And sure enough, right, my Na ended up with the nitrate, and if I take a look at this, my H plus did end up with the bicarbonate. So I have two hydrogens. Instead of bicarbonate, I have hydrogen carbonate. And then as a side note, I put parenthetically, this stuff decomposes into water and CO2, but I just left it there so we could kind of see it a little bit better. Yeah, hydrogen carbonate, a carbonic acid automatically, spontaneously decomposes into water and CO2. It's the same stuff. So this then, in fact, would be, right, it would be a acid-base reaction. Where in this case it looks like this is my acid here on the left, it had the H+, this is what accepted it, so that would be my base. And then lastly, let's look at this one, is this acid base or not? This one's set up a little bit differently. But in this case I have the thing with the H, so if I look over here on the right hand side, it looks like I had HF, but now it's just F minus 1. So this thing had the H+, and really it looks like this just went over to here. So I didn't really do a double replacement in this case, but right, this thing had, over here the hydrogen phosphate had one H, and now it has two H's, right? Here it had one, here it has two. So it looks like that picked it up. Or in other words, that this acted as the acid, and this acted as the base, right? The HF gave an H to the hydrogen phosphate to have the dihydrogen phosphate, and then we're just left with the fluoride. So this would still be considered acid-base because we transferred a proton. Right? So this would also be an acid-base reaction. Right? All we're looking for is a transfer of a proton. So that's how to kind of identify your acid-base reactions. They're also fairly easy to spot. You just need to look for an H plus to move from one thing to another one. If you see an H plus move from one thing to another, then you've transferred it. It's an acid-base reaction. If you have any questions or comments, please leave them down below. Go practice this, and then keep an eye out for the next video, which is the redox reaction. So we're going to look at organic redox reactions. Happy studying.